In exercise 1, compute u plus v and u minus v. So for u plus v, that means we need to add minus 1 minus 3. So minus 1 plus minus 3. Then 2 plus minus 1. This will give us, it is equal minus 4 and 1. So this is u plus v. For u minus 2v, that's mean u minus 2v is equal. So u is minus 1, then minus 2v, that's mean 2 multiplied by minus 3. So here we have 2 multiplied by minus 3. Then for the second entry, here we have 2 minus 2 multiplied by minus 1. So this will give us, it is equal here minus 1, 2 multiplied by minus 3, minus 6. Here we have minus, so minus with minus will be plus. For this one here we have 2, then 2 multiplied by minus 1 will be minus 2, and here we have minus, so this will be plus. This will give us, it is equal 5 and 4. So for sketching in exercise 3, display the following vectors using arrows on the xy graph. We need to sketch u, v, minus v, minus 2v, u plus v, u minus v, and u minus 2v. And here we have our vectors u and v, which is in exercise 1, which is minus 1, 2 for u, and minus 3, minus 1 for v. So let us first sketch the vector u, which is minus 1, 2. So here we have minus 1, 2. So this is a sketch for the vector u. This one is u. Now for v, we have minus 3, minus 1. So here minus 3, and for this one should be here minus 1. So here minus 3, minus 1. So this is minus 3, approximately here also minus 1. So we said here it is minus 1. So this is v. Then we need to sketch minus v. For the vector minus v, it is the same vector of v, just it is in the opposite direction. So minus v, if v is equal minus 3 minus 1, v will be 3, 1, which is here. So it is in the opposite direction, but the same length. So this one is minus v. Then we have the vector minus 2v. Minus 2v, that means it is, if we multiply this one by minus 2, we'll get it is 6. So minus 2v is equal 6. And this one minus 2 minus 1 will be 2. So the point is 6 and 2. 6 and 2 should be in the same direction of the v of minus v, but the length is duplicated by 2. So this is minus 2v. Then we have the vector u plus v. We said in the exercise number 1 that u plus v is minus 4 and 1. So minus 4 here, 1 here, so this one is u plus v. Then we have u minus v. For u minus v, here we have u, here we have v, so u minus v should be equal to minus 1 minus minus 3 would be minus 1 plus 3, which is 2. Then 2 minus minus 1, so it will be 2 plus 1, which is 3. So the vector is 2, 3. So this one for u minus v. Then we have the vector u minus 2v. So u minus 2v should be the vector 5, 4. So this is 5, and here we have 4, this one. So this one for u minus 2v. In exercise 5 and 6, write a system of equations that is equivalent to the given vector equation. So here we have x1 multiplied by the vector 6 minus 1, 5, plus x2 multiplied by the vector minus 3, 4, 0. It is equal 1 minus 11 minus 5. We need to rewrite this one as a system of equation. So multiply x1 by 6 plus x2 multiplied by minus 3 is equal 1. So for the first equation we have 6x1 minus 3x2, it is equal 1. Then for the second row here we have x1 multiplied by minus 1 plus x2 multiplied by 4 is equal minus 7. So this is minus x1 plus 4x2, it is equal minus 7. Then the last equation, x1 multiplied by 5 plus x2 multiplied by 0, it is equal minus 5. So here we have 5x1. For x2, if we multiply 0 by x2, this will give us 0. So it is equal to then minus 5. Now we have this is a system of linear equation. In exercise number 7, we asked to use this figure to write each vector listed in the exercise as a linear combination of u and v. Is every vector in R2 a linear combination of u and v? So let us see first the vector a. So here if we write here 7, then we have the vector a. Let us see the vector a. The vector a is here, which is this one. So we need to rewrite it as a linear combination of the vector of u and v. So here a is equal. If we see this one, a is far from the x-axis. Here we have minus v minus 2v, then we reach to this one. And for this one, this direction, we have here u. So it is far by minus 2v and u. So e should be a is equal minus 2v plus u. يعني أنا أشوف النقطة ال A اللي هي عند ال head of A، ألاحظ إنه من هنا يبعد minus 2v ومن this direction يبعد اللي هو ال u. فالنقطة هذه تقاطع عبارة عن ال head لل u وال head ل minus 2v. فلما أجي أجمع minus 2v plus ال u بيصير عندي هذا minus 2v بلس اليو. إذا اليو بشيله هنا بخليه عند التيل تبع اليو، أخليه عند الهيد تبع minus 2v. فاللي يتكون عندي اللي هو هذا using parallelogram اللي بيتكون عندي اللي هو الفيكتور A. So A is equal minus 2v plus اليو. So now let us see another vector. Then we have B, the vector B. So B is equal, where is B? We have B, this one, this vector B. So this is intersection between, if we add minus 2v, because in the same parallelogram, and the vector, so here from here minus 2v, and for this one, if we add from minus 2v until this one we have u, then from this point to this one another u. So B is minus 2v plus 2u. يعني أنا عندي النقطة اللي هي B هذه تمثل لي الفيكتور. فبشوف أول شيء النقطة هذه التقاطع عبارة عن إيش؟ بشوف من هنا هي عبارة عن minus 2v لحد هنا، بحيث إنه يكون عندي موازي للنقطة هذه. بلس لما أجي أجمع هذا عبارة عن u وهذا عبارة عن u. إذا البي عبارة عن minus 2v plus 2u. نيجي نشوف C. So C is equal. C موجود عندي هنا. إذا أشوف النقطة اللي توازيها تقريبا عند هنا. اللي هي هذه. إذا هذا عبارة عن minus v minus 2v minus 3v تقريبا minus 3.5 في ال v. إذا عبارة عن minus 3.5v. نشوف اليو كم واحدة محتاجين. هذا عندي 1 وهذا عندي 2. إذا minus 3.5v plus 2u. So this is the vector C. Then we have the vector D. So D is equal. Where is D? This one is D. So بالنسبة لدي عندي هنا اللي هي minus v minus 2v 3v لحد هنا اللي هي آخر نقطة على نفس المستوى 4v. إذا عندي minus 4v. طيب محتاجين كم u على أساس نوصل عند الدي؟ فبيصير هنا عندي 1u 2u 3u. So minus 4v plus 3u. So this is the vector A, B, C, D using this graph. Since u and v are not يعني عندي ال u وال v they are not multiple of each other because this is u, this is v, it is not multiple of each other. So if in exercise number 9, write a vector equation that is equivalent to the given system of equations. So here we have a system of linear equation. We need to rewrite it as a vector equation. So we know that the vector equation x1 multiplied by a1 plus x2 multiplied by a3, a2 plus x3 multiplied by a3 is equal to b. So here we have x1 multiplied by the vector a1, which is the coefficient of x1 here 0, then the coefficient of x1 here 4, and the coefficient of x1 which is minus 1. Then plus x2 multiplied by the coefficient of x2 in all three equations. So here we have 1, 6, 3. Plus x3 multiplied by the coefficient of x3 in all three equations. So here we have 5 minus 1 minus 8. This is equal to the vector b, which is 0, 0, 0. So this is a vector equation of the system in exercise number 9. So now let us see number 11. In exercise 11 and 12, determine if P is a linear combination of A1, A2 and A3. So if he asked to determine if it is a linear combination, that means we need to check, is the system consistent? If the system consistent, that means B is a linear combination. Otherwise, it will be not a linear combination of the given vectors. So let us do here number 11. First, let us rewrite it as a matrix. So we have A1, which is 1, minus 2, 0, then A2, 0, 1, 2, and we have A3, 5, minus 6, 8, and B, here we have 2, minus 1, 6. So this is our matrix. We need to do row operation for this matrix to check if P is a linear combination or not. So we can first do the row operation, row 2. We need to get rid of this minus 2. So row 2 will be equal to row 1 plus row 2. This will give us here 1, 0, 5, 2. Then 2 multiplied by 1, 2, then we add it with minus 2, this will give us 0, this one will give us 1, this one will give us 4, this one is 3, and here we have 0, 2, 8, 6. So now we need to get rid of these two to be 0, so that means we need to do another row operation. So row 3 will be equal minus 2 row 2 plus row 3, and we get this new matrix which is 1 0 5 2, then 0 1 4 3, and row 3 we replace it by minus 2, row 2 plus row 3 we get it is 0 0 0 0. So it is clear here that the system is consistent, so that's mean B is a linear combination of the vectors a1, a2, a3. So right here, since the system is consistent, then B is a linear combination of a1, a2, and a3. So asking whether the system consistent or B is a linear combination, it is just the same. We need to do row operation. If the system consistent, B is a linear combination. If the system is inconsistent, so B it will be not a linear combination of that system, of that vector, sorry. In exercise 13 and 14, determine if B is a linear combination of the vectors formed from the columns of the matrix A. So again, here asking about is B a linear combination. That's mean similarly if he asked if the system is consistent or inconsistent. So let us rewrite this one as a matrix. So here we have our matrix will be 1 0 minus 2 minus 4 3 8, then 2 5 minus 4, and here we have the piece 4 minus 7 minus 3. We need to do some row operation to see if this system is consistent or inconsistent, and then we can determine if B is a linear combination or not. So let us get rid of this minus 2. So from here, row 3 is equal to row 1 plus row 3. The new matrix is, here we have 1 minus 4, 2, then 3, 0, 3, 5, minus 7, and for the last row we replace row 3 by 2, row 1 plus row 3, and we get it is, here we have 0, then 0, then 0, then 3. Since the system from here it is inconsistent because we have this form, so that's mean B is not a linear combination of the matrix of the columns of the matrix A or the vectors in a matrix A. So we conclude here, since the system is inconsistent, B is not a linear combination of vectors in A. So because the system inconsistent, that means B is not a linear combination of the vectors in the matrix A. In exercise 15, list 5 vectors in span v1, v2. For each vector, show the weights on v1 and v2 used to generate the vector and list the 3 entries of the vector. Do not make a sketch. So here we are given vector v1 and v2. We want to write or list 5 vectors in this span, so we need to make 5 linear combinations of vector v1 and v2. For example, let us choose the first linear combination, for example 0 v1. This is 0 vector, or sorry, 0 scalar, plus 0 v2. This will give us, it is equal to the vector 0, 0, 0. If we choose another linear combination, which is, for example, 1 multiplied by v1 plus 1 multiplied by v2, this will give us the vector v1 plus v2. 7 minus 5 will be 2, 1 plus 3 will be 4, minus 6 plus 0 will be minus 6. If we choose another linear combination, for example, 0 multiplied by v1 plus 1 multiplied by v2, this is just the vector v2, which is minus 5, 3, 0. Then if we write another linear combination, for example, 1 multiplied by v1 plus 0 multiplied by v2, this will give us the vector v1 only, which is 7, 1, minus 6. If we choose another linear combination, for example, 2v1 plus 2 multiplied by v1 plus, for example, 1 multiplied by v2, that's mean we multiplied the vector v1 by 2 and then we add it with v1, sorry, we multiplied 2 by v1 and then we add it with the vector v2, and we get here it is equal, here we have 9, then 5, then minus 12. So you can write infinitely many linear combinations of the vector v1 and v2, just you change the scalar. So in general, you rewrite this one, you rewrite it as p is equal x1 multiplied by v2 plus x2 multiplied by v2. You can choose any x1 and any x2, and then you do this operation to find what is the vector p, which is inside the span v1 and v2. So in 17, let a1 is equal 1, 4, minus 2, a2 is equal minus 2, minus 3, 7, and b is equal 4, 1, h. For what values of h is b in the plane spanned by a1 and a2? So if we have two vectors, which is a1, a2, and we have the vector b, we need to choose a value for h that make our system is consistent, or that make p is in the plane spanned by a1 and a2. So the first step, we need to write the matrix formed by a1, a2, and b. Then we need to do some row operation to know what is the case or what is the value of h that make our system consistent. So here 4, 1, h. We need to do row operation to reduce this matrix. So after doing row operation for the matrix, we get the final matrix, which is this one. So the system is consistent whenever 17 plus h is not equal to any value different than 0. So from here we see that 17 plus h, let us choose different color, for example, here 17 plus h is equal to 0, that's mean h is equal minus 17. So b is in the plane spanned by a1 and a2 if and only if h is equal minus 17. Because if h is not equal minus 17, for example, let us take it 1. So if h is equal 1, we get the form 0, 0, b. That's make our system is inconsistent. Because we want the consistent system, that means 17 plus h should be equal to 0. That means our h should be equal minus 17. In 19, give a geometric description of span v1, v2 for the vectors in v1 and v2. We know for the geometric description, if we write here, for example, here geometric description for two vectors, if the vectors are linear combination of each other or is a multiple of each other, for example, if we can write v1 is equal sorry, V1 is equal CV2 for any C where C is in R. That's mean the geometric description is a line through V1 and the origin, which is 0, 0. But for the case if V1 cannot be written as CV2, that's mean we have the geometric description which is a plane spanned by V1 V2. يعني إذا كان التو vectors multiple of each other، واحد منهم أقدر أكتبه عن طريق CV2 بحيث أنها C could be any real number، إذا بيكون عندي عبارة عن a line through V1 and the origin. لكن في الحالة اللي ما أقدر أكتب فيها إنه الفيكتور عبارة عن الفيكتور الأول يساوي C multiplied by الفيكتور الثاني، إذا الجيومتريك description راح يصير عبارة عن a plane. البلين هذا spanned by the vector V1 and V2. فناو we have V1 is equal A2 minus 6, V2 is equal 12, 3 minus 9. Can we write the vector V1 as CV2? So from here it is clear that إنه V1 or V2 it is equal 3 over 2 V1. Because if we take 3 over 2 and multiply it by V1, we get the vector V2. So here, if we evaluate 3 over 2 V1, 3 over 2 V1, this will give us 3 over 2 multiplied by 8, which is 12. 3 over 2 multiplied by 2, which is 3. 3 over 2 multiplied by minus 6, which is minus 9. This one gives us V2. So we can rewrite these two vectors as one vector multiple of each other. يعني أنا قدرت أكتب إنه الفيكتور 2 عبارة عن 3 over 2 V1. إذا أنا أعرف إنه الفيكتور 1 والفيكتور 2 are in the same line because each of them multiple of the other. ممكن أنا أكتبها V2 is equal 3 over 2 V1 or ممكن أكتبها بصيغة ال V1 اللي هي ال V1 is equal 2 over 3 V2. يعني ممكن أكتبها بهذا الشكل أو بالشكل المغاير اللي هي عندي هنا، أو ممكن إن أكتبها V1 is equal 2 over 3 V2. فلو أقدر أكتبها بهذا الشكل سواء هذا الشكل أو هذا الشكل اثنيناتهم تعطيني نفس الناتج. فالgeometric description is a line. We said here it is a line, or let us write a span. It is span UV, V1, V2 is the set of points on the line V1 and 0, which is the point origin 0, 0, because we have here V2 is a multiple of V1. Give a geometric description of span V1, V2 for the vectors in exercise 16. The vectors in exercise 16 was, we have V1 is equal 3, 0, 2, and we have V2 is equal minus 2, 0, 3. These two vectors, they are not multiple of each other because we cannot write V1 is equal CV2 for any C in R. يعني احنا ما نقدر نكتب الفيكتور V1 as a multiple of the vector اللي هي V2. That's mean إنه V2 is not a multiple of V1. And from here we conclude that إنه span V1, V2 is a plane. According to the previous chart, we said if they are not a multiple of each other, so the span V1, V2 is a plane in R3, because here we have 3 entries in each vector through the origin. For 21, it says let u is equal to minus 1, v is equal to 1, show that hk is in span uv for all h and k. So we want to show that this matrix, which is contain u, v, and hk, is consistent for any value of h and k. So first, let us rewrite this one as a matrix. So here we have 2 minus 1, then 2, 1, and here we have hk. We need to do row operation for this matrix to rewrite it as in echelon form or in reduced echelon form. So for example, if we replace row 1 by, or row 1 is equal half row 1, this will give us 1, 1, half h, and here we have minus 1, 1 k. Then if we do the second row operation, that's row 2 is equal row 1 plus row 2. This will give us, here we have 1, 1, half h. So 1 plus minus 1, 0. This will give us 2. This will give us half h plus k. Now to make this one to be 1, we can write row 2 is equal half row 2. This will give us here 1, 1, half h, then 0, 1, 1 over 4 h plus 1 over 2 k. Now this system is consistent for the case if this one is equal to 0, the system will be consistent because here we have x2 is equal to 0. If this one is not equal 0, for example, it is equal 3 or 4 or any other value, also the system is consistent. So from here, it is clear that this system is consistent for any value of h and k. And from here, we say that for any value of h and k, they are in the span uv. So half k plus 1 over 4h can be any value for the system to be consistent. So from here we conclude that hk is in span uv for all h and k. So let us write this one as a general result. So here 1 over 4 h plus 1 over 2 k can be any value for the system to be consistent. So the vector hk is in span uv for all h and k. In 23, we need to mark each statement true or false and justify our answer. So the first statement, another notation for the vector minus 4, 3 is minus 4, 3. This one we said it is false because this is a matrix of 2 by 1, and this is another matrix which is 1 by 2. We said another form for the vector minus 4, 3 is the point minus 4, 3, not the matrix minus 4, 3. Then the points in the plane corresponding to -2, 5 and -5, 2 lie on a line through the origin. This is not the case because here we have -2 and 5 is not a multiple of -5 to 2 to be the same in the same line. So this one is false since -2, 5 is not a multiple of 5 minus 2. يعني هو يقول هنا عندي إنه البوينت -2 و 5 والبوينت -5 و 2 موجودات in the same line through the origin. طبعا هي not the case لأنه لازم يكونوا بثنتينتهم واحدة منهم multiple of each other على أساس إنه يصير عنده في نفس اللاين. لكن هنا بما إنهم عندي -2 5 is different than -5 and 2, none of them is multiple of each other. إذا هذه ما راح تكون line through the origin، راح تصير plane spanned by اللي هي الفيكتور -2 5 و -5 2. C. An example of a linear combination of vector v1 and v2 is the vector half v1. This is true because إنه any vector اللي هو ممكن أنا أكتب half v1 اللي مثلا لو كانت عندي y is equal half v1 plus 0 v2. هذه نفس الشيء تعتبر linear combination اللي هي في الأخير راح تطلع لي اللي هي half v1. So this one is true. D. The solution set of a linear system whose augmented matrix is A1, A2, A3, B is the same as the solution set of the equation x1, A1 plus x2, A2 plus x3, A3 is equal B. This one is true. لأنه نحن قلنا لما يكون عندي اللي هي solution set of this form اللي هي vector matrix نفسها لما يكون عندي solution set of this matrix. So this one is true. E. The set span UV is always visualized as a plane through the origin. This one false. إذا كان U وال V multiple of each other راح يصير عندي إيش؟ a line. أما إذا كان U و V are not a multiple of each other راح يصير عندي اللي هي plane. إذا ممكن هنا نكتب false وهنا span UV is not a plane if V is a multiple of U or when U is equal or when U is the zero vector. لأنه قلنا لو كان عندي one of them multiple of each other راح يصير عندي line، بينما لو كانت ال U وال V ما بينهم علاقة يعني ما multiple of each other راح يصير عندي اللي هو plane. فهذه ما always as a plane، ممكن نقول often. For 24 also we need to mark if the statement is true or false and we need to justify our answer. So any list of 5 real numbers is a vector in R5. This one is clear, it is true. Then the vector U results when a vector U minus V is added to the vector V. Let us see this one. So here we have B. If we add the vector U minus V with the vector V, so U minus V plus V, this will give us minus V plus V 0, and here we get the vector U. So this one is true. That's because U minus V plus V is equal to U. Then C, the weights C1 until CB in a linear combination C1V1 plus CBVB cannot all be 0. This one is false. Why? Because we said the 0 vector is in all linear combination. So this one is false, because if all zeros we get a 0 vector which is a linear combination of a set of vectors. Because of all of them 0, we get the 0 vector which is in the linear combination. So D, when U and V are non-zero vectors, so both of them are non-zero. Span UV contains the line through U and the origin. We say this one also false because if they are not multiple of each other, the span is a plane. But if they multiple of each other, so that means the span is a line. So this is false. We said here span UV can be a plane. E, asking whether the linear system corresponding to an augmented matrix A1, A2, A3, B has a solution amounts to asking whether B is in span A1, A2, A3. We said this is the same, so that means this statement is true. In 25, let A is the matrix, and here we have B a vector. Denote the columns of A, B, and the vector we have A1, A2, A3, and let W be span A1, A2, A3. We asked the first one, is B in A1, A2, A3, and how many vectors are in A1, A2, A3? If we ask is B in A1, A2, A3, that's mean no, because the A1, A2, A3 is the set of 3 vectors only. So this is the first one is no. And how many vectors are in A1, A2, A3? This is 3 vectors. Because this is the set of vectors, not a span. So is B in the set A1, A2, A3? No, because it is not one of these vectors. Because here we have 4, 1, minus 4. None of this one is 4, 1, minus 4. So this is no. Is B in W? W represents the span of A1, A2, A3. We need to check. Is this system consistent? If it is consistent, that means B, yes, is in W, which is in the span. But if the system is inconsistent, so B shouldn't be in the span. So for B, we need to write the matrix, and then we need to do some row operations to know if the system consistent or inconsistent. So minus 4, minus 2, 3. Then we have B4, 1, minus 4. We do some row operation to reduce this form to the echelon form. So it is clear here that the system is consistent. So B is in W, which is in the span A1, A2, A3. And for part B, how many vectors are in W? W is the set of all linear combination. So W has infinitely many. So for B, since the system is consistent, yes, B is in W. B is in W, and W has infinitely many vectors. For part C, show that A1 is in W, hence row operations are unnecessary. How can we show that A is in W? We know that we can write A1 is equal 1 multiplied by A1 plus 0 multiplied by A2 plus 0 multiplied by A3, because it is a linear combination of A1, A2, and A3 with the weight 1, 0, 0 respectively. So A1 is in W because we can write A1 as a linear combination of the 3 vectors which is in W. For 26, let A is equal, we are given here a matrix A and B is a vector, and let W be the set of all linear combination of the columns of A. Is B in W? and then we need to show that the third column of A is in W. To show that is B in W, that means we need to show that this matrix, which is AB, is consistent. If it is consistent, that means it's B in W, and if it is not consistent, so the B is not in W. So let us do row operation and see what is the case of this system, consistent or inconsistent. So after rowing operation, do row operation for this matrix, we see that the system is consistent, and from here we say that for A, the system is consistent. From here, that's mean B is in W. For part B, show that the third column of A is in W. So that means we need to show that this column 6, 5, 1 is in W, which is the set of all linear combinations. So we can write A3, which is the third column, as 0 multiplied by A1 plus 0 multiplied by A2 plus 1 multiplied by A3, which is show that it is a linear combination of A1, A2, and A3.